Yes, there is a maximum distance for conductor runs from a transformer to switchgear. The code reference is NEC 2020, Article 450.3b. The maximum distance is 75 feet or 22.9 meters. The maximum distance applies to the total length of the conductors, including both hot and neutral conductors. This distance limit is intended to minimize voltage drop and heat buildup in the conductors. If the distance exceeds 75 feet, additional calculations may be required to ensure that the voltage drop and heat dissipation remain within acceptable limits. For longer runs, it may be necessary to increase the conductor size or install intermediate tap points. This distance limit may vary depending on the specific requirements of the transformer and switchgear used. Always refer to the manufacturer's instructions and consult with a qualified electrician for specific guidance. To elaborate, let's delve deeper into the rationale behind this 75-foot restriction and its implications for electrical installations. Firstly, the primary reason for limiting the conductor distance is to mitigate voltage drop. Voltage drop refers to the reduction in voltage that occurs along a conductor due to its resistance. As electricity flows through a wire, some of the electrical energy is converted into heat due to the wire's inherent resistance. This energy loss manifests as a decrease in voltage at the load end of the conductor. Excessive voltage drop can lead to various problems, including reduced equipment performance, overheating of conductors, and even equipment malfunction. Secondly, heat buildup is another significant concern. When conductors carry electrical current, they generate heat. The amount of heat generated is proportional to the square of the current and the resistance of the conductor. If the conductor run is too long, the heat generated may exceed the conductor's ability to dissipate it, leading to overheating. Overheated conductors can damage insulation, reduce conductor lifespan, and even pose a fire hazard. Article 450.3b of the National Electrical Code, or NEC, specifically addresses the protection of transformers. This section outlines requirements for overcurrent protection of transformers to prevent damage from overloads and short circuits. The 75-foot rule is a part of these protective measures, ensuring that the conductors connecting the transformer to the switchgear are adequately sized and protected. If the conductor run exceeds 75 feet, the NEC requires additional calculations to ensure that the voltage drop and heat dissipation remain within acceptable limits. These calculations typically involve determining the appropriate conductor size based on the load current, conductor length, and allowable voltage drop. The allowable voltage drop is usually specified as a percentage of the nominal voltage, typically 3% for branch circuits and 5% for feeders. To perform these calculations, electrical engineers and electricians use various formulas and tables provided in the NEC. One common formula for calculating voltage drop is voltage drop equals 2 times K times I times D divided by circular mils, where K is the direct current resistance for the conductor material, I is the current in amps, D is the one-way distance in feet, and circular mils is the cross-sectional area of the conductor. The value of K varies depending on the conductor material. For copper, K is typically around 12.9 ohms circular mils per foot. For aluminum, K is typically around 21.2 ohms circular mils per foot. Circular mils can be found in NEC tables. If the voltage drop exceeds the allowable limit, the conductor size must be increased to reduce the resistance and lower the voltage drop. Alternatively, intermediate tap points can be installed along the conductor run to reduce the effective length of the conductors. In addition to voltage drop calculations, it is also important to consider the ampacity of the conductors. Ampacity refers to the current carrying capacity of a conductor. The NEC provides tables that list the ampacity of various conductor sizes based on their insulation type and installation conditions. The conductor ampacity must be sufficient to carry the load current without overheating. If the conductor run is exposed to high ambient temperatures or is installed in a confined space, the ampacity may need to be derated to account for the reduced heat dissipation. The NEC also specifies requirements for conductor insulation. Conductors must be insulated to prevent electrical shock in short circuits. The type of insulation required depends on the voltage, temperature, and environmental conditions. Common insulation types include thermoplastic high heat nylon, cross-linked polyethylene, and rubber. When selecting conductors for a transformer to switchgear connection, it is crucial to consider not only the electrical requirements but also the mechanical and environmental conditions. The conductors must be able to withstand the stresses of installation and operation, including vibration, bending, and exposure to moisture, chemicals, and ultraviolet radiation. Furthermore, proper termination and splicing techniques are essential to ensure a reliable and safe connection. Conductors must be terminated using appropriate connectors that are listed for the conductor size and material. Splices must be made using approved splicing methods that provide adequate mechanical strength and electrical conductivity. It is also important to consider the grounding requirements for the transformer and switchgear. Grounding provides a low impedance path for fault current to flow back to the source, helping to trip over current-protected devices and prevent electrical shock hazards. The NEC specifies detailed requirements for grounding transformers and switchgear, including the size and type of grounding conductors and the location of grounding electrodes. In summary, the 75-foot rule for conductor runs from a transformer to switchgear is a critical safety measure designed to minimize voltage drop and heat buildup in the conductors. Exceeding this distance requires additional calculations to ensure that the voltage drop and heat dissipation remain within acceptable limits. Electrical engineers and electricians must carefully consider all relevant factors, including conductor size, ampacity, insulation, termination, and grounding, to ensure a safe and reliable electrical installation. Remember that this is a general overview, and the specific requirements may vary depending on the specific application and local codes. Always consult with a qualified electrician or electrical engineer for specific guidance on your project. Let's examine some specific scenarios where the 75-foot rule might come into play. Imagine a scenario where a large industrial facility is installing a new 1000 kV transformer to power a section of its manufacturing plant. The transformer is located in a substation outside the main building, and the switchgear is located inside the building, approximately 100 feet away. In this case, the conductor run from the transformer to the switchgear exceeds the 75-foot limit specified in NEC 450.3b. Therefore, the electrical engineer must perform voltage drop calculations to determine the appropriate conductor size. The engineer would consider the load current, conductor length, and allowable voltage drop to calculate the required conductor size. If the calculations indicate that the voltage drop would exceed the allowable limit with the initially selected conductor size, the engineer would need to increase the conductor size or consider installing intermediate tap points. Another scenario might involve a commercial building with a roofed-up transformer serving a distribution panel on a lower floor. The vertical distance between the transformer and the distribution panel could easily exceed 75 feet, especially in taller buildings. In this situation, the electrician would need to carefully consider the voltage drop and ampacity of the conductors. The electrician might also need to direct the ampacity of the conductors if they are installed in a conduit or raceway that is exposed to sunlight or high ambient temperatures. In both of these scenarios, it is crucial to document all calculations and design decisions to demonstrate compliance with the NEC and other applicable codes and standards. This documentation should include the conductor size, ampacity, voltage drop calculations, and any dating factors that were applied. Now let's discuss some practical tips for minimizing voltage drop and heat buildup in conductor runs. Firstly, use the largest conductor size that is practical and economical. Larger conductors have low resistance, which reduces voltage drop and heat generation. Secondly, keep conductor runs as short as possible. The shorter the conductor run, the lower the voltage drop and heat generation. Thirdly, use conductors with lower resistance materials, such as copper. Copper has a lower resistance than aluminum, which means it will have less voltage drop and heat generation for the same conductor size and current. Fourthly, install conductors in a manner that promotes heat dissipation. Avoid installing conductors in enclosed spaces or in direct sunlight, as this can reduce their ability to dissipate heat. Fifthly, use proper termination and splicing techniques. Loose or corroded connections can increase resistance and generate heat. In addition to these practical tips, it is also important to regularly inspect and maintain electrical connections to ensure that they are in good condition. Loose connections should be tightened, and corroded connections should be cleaned or replaced. Regular inspections can help to identify potential problems before they become serious hazards. Let's also consider the role of technology in managing conductor runs and mitigating voltage drop. Modern electrical design software can automatically calculate voltage drop and ampacity for conductor runs, taking into account various factors such as conductor size, length, and installation conditions. This software can help electrical engineers and electricians to optimize conductor sizes and minimize voltage drop. Furthermore, advanced monitoring systems can continuously monitor voltage levels and conductor temperatures, providing early warning of potential problems. These systems can help to prevent equipment damage and improve electrical safety. It's also important to remember that the NEC is not the only source of information on conductor runs. Manufacturers of transformers and switchgear often provide specific recommendations for conductor sizes and installation practices. These recommendations should be carefully considered in addition to the NEC requirements. In addition to the technical aspects of conductor runs, it is also important to consider the safety aspects. Working with electrical conductors can be dangerous, and it is essential to follow proper safety procedures to prevent electrical shock and other injuries. Always de-energize circuits before working on them, and use appropriate personal protective equipment such as insulated gloves and safety glasses. If you are not qualified to work on electrical conductors, hire a qualified electrician to do the work. The information presented here is intended for educational purposes only and should not be considered a substitute for professional advice. Electrical codes and standards are constantly evolving, and it is important to stay up to date on the latest requirements. Always consult with a qualified electrician or electrical engineer for specific guidance on your project. Let's talk about the implications of using aluminum versus copper conductors for these runs. While copper is generally preferred due to its lower resistance, aluminum conductors are often used in larger sizes to reduce cost and weight. When using aluminum conductors, it is crucial to select the appropriate conductor size to compensate for its high resistance. Aluminum conductors also require special connectors and termination techniques to prevent corrosion and ensure a reliable connection. These connectors are typically made of aluminum or are bimetallic to prevent galvanic corrosion between the aluminum conductor and the copper or other metal of the connector. Galvanic corrosion occurs when two dissimilar metals are in contact in the presence of an electrolyte, such as moisture. The more active metal will corrode preferentially, which can weaken the connection and increase resistance. To prevent galvanic corrosion, it is important to use connectors that are specifically designed for use with aluminum conductors and to follow the manufacturer's instructions for installation. Another important consideration when using aluminum conductors is their higher coefficient of thermal expansion compared to copper. This means that aluminum conductors will expand and contract more with temperature changes than copper conductors. This can put stress on connections and terminations, potentially leading to loosening and increased resistance over time. To mitigate this issue, it is important to use connectors that are designed to accommodate thermal expansion and contraction. These connectors typically have spring-loaded or other mechanisms that maintain pressure on the connection even as the conductor expands and contracts. Let's now touch on the importance of proper labeling and documentation. All conductors, transformers, and switchgear should be clearly labeled with their voltage, current, and other relevant information. This labeling helps to prevent confusion and ensures that personnel are aware of the electrical hazards. In addition to labeling, it is important to maintain accurate documentation of the electrical system, including wiring diagrams, panel schedules, and equipment specifications. This documentation is essential for troubleshooting problems, making repairs, and performing maintenance. The documentation should be kept in a safe and accessible location and should be updated whenever changes are made to the electrical system. Consider the impact of harmonic currents on conductor sizing and voltage drop. Harmonic currents are currents with frequencies that are multiples of the fundamental frequency, typically 60 Hz. These currents can be generated by nonlinear loads such as electronic devices, variable frequency drives, and uninterruptible power supplies. Harmonic currents can cause a variety of problems, including increased conductor heating, transformer overheating, and voltage distortion. To mitigate the effects of harmonic currents, it may be necessary to increase the conductor size or use special harmonic filters. The NEC provides guidelines for sizing conductors to account for harmonic currents. Let's briefly address the use of shielded conductors in sensitive applications. Shielded conductors have a conductive layer that surrounds the insulated conductors. This shield helps to block electromagnetic interference, or EMI, from entering or exiting the conductors. Shielded conductors are often used in sensitive electronic circuits and communication systems where EMI can cause problems. The shield is typically grounded to provide a path for the EMI to flow to ground. Choosing the right type of conduit or raceway for conductor runs is also essential. Conduit and raceway provide mechanical protection for conductors and help to prevent electrical shock hazards. The type of conduit or raceway required depends on the application and the environmental conditions. Common types of conduit include rigid metal conduit, intermediate metal conduit, electrical metallic tubing, and flexible metal conduit. Raceways can be metal or non-metallic and come in various shapes and sizes. When selecting conduit or raceway, it is important to consider its resistance to corrosion, mechanical strength, and fire resistance. It is vital to understand the role of overcurrent protection devices, such as circuit breakers and fuses, in protecting conductors from overloads and short circuits. Overcurrent protection devices are designed to interrupt the flow of current when it exceeds a predetermined level. This helps to prevent conductors from overheating and potentially causing a fire. The NEC specifies requirements for the size and type of overcurrent protection devices based on the conductor ampacity. It's also essential to coordinate overcurrent protection devices to ensure that the device closest to the fault will trip first, minimizing the impact on the rest of the electrical system. Finally, let's stress the importance of ongoing training and education for electrical professionals. Electrical codes and standards are constantly evolving, and it is important for electricians and electrical engineers to stay up to date on the latest requirements. Ongoing training and education can help to ensure that electrical work is performed safely and in compliance with the latest codes and standards. Many organizations offer training courses and certification programs for electrical professionals. Remember that working with electricity can be dangerous, and it is important to follow proper safety procedures at all times. If you are not qualified to perform electrical work, hire a qualified electrician to do the job. These points are intended to broaden awareness and not be a replacement for NEC regulations. Also remember to check the transformer and switchgear documentation for specific requirements and limitations.